Hello everyone, this is Captain Viveksheel Srivastav and welcome back. So now today we'll continue further from the topic that we had left last time. Last time we had discussed the need for transferring data from a globe to a two-dimensional paper chart, and we had also learnt about what was departure. Alright, so today we'll continue further and we'll see how we can develop Mercator charts from the globe. Okay, so today the topic is development of Mercator charts, how Mercator charts are developed, and going further we will learn about what is meridional parts and what is DMP, difference in meridional parts. So these two things are very important for the construction of Mercator charts. Okay, so like we did last time, I'll just refresh a little bit. Okay. So last time we were trying to figure out stripping out these sections of paper from the globe and pasting it on a two-dimensional plane on a chart. Okay, and as we had seen last time, it will come out something like this. All right. Now there are gaps and the chart is not complete, it's not continuous. The continuity is broken in the chart. Okay, so now to construct a seamless chart so that we can navigate all through, we can plot our courses all through, we need to join these areas and we need to make a seamless chart. So let's see how we go about doing it. All right, so let's consider two meridians. Let's two meridians at with the difference of 1 degree. So between these two meridians you have a d long of 1 degrees. Okay, so 1 degrees d long means 60 minutes of d long. Okay, let's assume that we are drawing on a scale of 1 minute is equal to 1 centimeter, just for simplicity sake. Okay, so now this is be our longitude scale. So what it means is that 1 minute of longitude is equal to 1 centimeter on this plane. So this distance is, this will be 60 centimeter at the equator. Okay, so on the chart this is 60 centimeter, and now imagine we've got at 40 degrees north latitude, we've got a square piece of land. Now I am exaggerating it so that we can see and we can understand the concept. Although 1 degree of longitude will be very less in proportion to the length, height. Okay, so this is just an exaggerated diagram to understand. So now this square piece of land at 40 degrees north latitude, the d long will be same 60 minutes for these two meridians because they are passing through the square. Now the departure over here at 40 degrees north latitude, which we have seen, departure is equal to d long into cos of latitude. Okay, so when you find out, the departure will come around 46 miles approximately. So if I have a d long of 60 minutes at 40 degrees north latitude, I'll have a departure of 46 miles. Now, because this area is quite small, 46 miles. So as I said earlier in my last video, that for smaller areas, they are practically flat, considered flat. So, and since the latitude difference is very less, this square can be safely considered as 46 miles, having one side as 46 miles, this one. And now, since we have assumed a square, the DLAT will be also 46 minutes. Okay. Now, since this is still a part of the globe, on the globe, the mile is constant everywhere. If I say my scale is 1 minute is 1 centimeter at the equator, here 1 minute of latitude is also equal to 1 centimeter, and everywhere that 1 minute is equal to 1 centimeter, whether we take it on latitude or longitude. All right. So a square is a square over here. Now, and our latitude scale is also the same. 1 minute is 1 centimeter. So distances measurement is not a problem. Everywhere you measure the distance is same, whether you measure here or here, in all directions, at all places, it will come out same. Now, but the problem is, now when we transfer this, let's first transfer it. So the bearings taken on these meridians at different locations will be different. Suppose at here this thing is 90 degrees, and if I have a 45 degrees bearing, it will be somewhat like this. But as the latitude increases on this chart, the 45 degrees will not be 45 degrees, because this is not 90 anymore. This is not 90 anymore, because the meridians are converging. So they'll make an angle like this. So your bearings and your courses will be different unless you take the meridian in the center. But at other places, it will be a problem to plot your courses and take your bearings. So for that purpose, now we need to straighten out the meridians. So what we do is, we try to, you think of this thing as a rubber sheet, as a sheet of rubber, and we try to stretch that rubber sheet. Let's see what happens. So this is the full chart, and I've got this d long over here, 60 centimeters, and I stretch these two meridians open, so that they become parallel. Okay. Now we try to make this square. What happens to the square when you stretch this square? It becomes a rectangle. That square is stretched in the east-west direction, and it becomes a rectangle. Now what happens to the rectangle? Now this is still 46 centimeters or 46 minutes, which is the DLAT. Now this has become 60 centimeters, right? Earlier it was 46 centimeters and we have stretched it, it has become 60 centimeters. So now we cannot keep this chart like this, because now earlier if I took a bearing of, suppose I am standing here and take a bearing of the other point, that bearing will be 45 degrees. But now the shape of that square landmass has changed. That square has become a rectangle. So now if on the chart I take a bearing of the other point, now this will not be 45, this will be much more than 45, maybe 50, 55 degrees something, right? So now my bearings will be wrong if I keep it like this. All right, so now this distortion that happens, this is the east-west distortion, okay? And yeah, and also you can see that departure, if it was here 46 miles, that departure has become 46 centimeter to 60 centimeters. So that departure has, the value of that departure has increased, but actual departure is 46 also only, right? So this distortion is also, we can say, is distortion in departure. The departure has been elongated. So in the east-west direction, okay. And how much is the distortion? If you see the ratio of distortion, what is the ratio of distortion? 46 has become 60. So 60 by 46. So, and what is this 60 by 46? 60 is d long, 46 was departure, and what is this? This value is secant of latitude. Departure upon d long is cos of latitude, and the d long upon departure is secant of latitude. So the distortion, east-west distortion, is proportional to secant of latitude. Okay, but now we have a problem. First of all, the bearings are not correct. Okay, secondly, the distances in the north-south direction are still correct, because on our scale, if we measure, the d lat is still 46 centimeter. So it is correct, coming correct on this scale. But the departure is not correct, coming correct on this scale that we have assumed. All right. And also the shape of the landmass has changed. So because now you can see that you have a square landmass as an island, and on the chart that landmass is looking rectangular. So there is a mismatch. You cannot identify points where to take bearing, and your bearings will be wrong. And so we cannot keep it like this, in this manner. So what we need to do is, we need to make this rectangle again a square, so that the shape of the landmass is retained. And that is the orthomorphic property of a Mercator chart. And it is very important to retain the shape, so that you can identify landmarks, your bearings are correct. Okay, so how do we do it? Now, to compensate for this distortion, we introduce a north-south distortion. So we elongate this rectangle to become a square again. So let's see how we go about it. Okay, so we have elongated it in the north-south direction to make it a square again. So now, what is the size of this square over here? And how much we have to elongate it? If this side was coming 60 and this is 46, I must make this 46 60, so it will become a square. So what we have done is we have made this 60 centimeters and this is 60 centimeters. All right. So now it is back a square, but although bigger than that square, but in size, but the shape is same. So now I take a bearing of the other end. Yeah, now it will come 45. If I see the square shape of landmass ashore and I see it on a chart, it matches. So there is no confusion. All right. So one problem is solved. Bearings and courses will be correct over here. But another problem remains now. First, the distance measurement in this direction has elongated, and because we have an east-west distortion, and now we have introduced a north-south distortion also. So even the DLAT has elongated now. So if we measure everything, all of this on our scale that we have assumed, so DLAT will be coming out to 60 minutes and departure is 60 minutes, 60 miles. But actually, in actuality, the square is 46 by 46. The landmass is 46 miles by 46 miles, not 60 by 60. All right. So now we have to solve this problem of measuring distance at that latitude after this east-west distortion and the introduced north-south distortion. So for measuring this, now we need to change our measurement scale. Okay, we know that this is 46 and this is 46, but on our scale what we are reading is 60 because we have this scale what we have defined, because we have taken longitude scale and earlier the latitude scale everything was same, so measurements were okay, but now we have distorted it. So now I need to modify my scale to read 60 centimeters as 46 minutes and 60 centimeters at 46 miles. All right. And by the way, now this north-south distortion is also in the same proportion as the east-west distortion. So this north-south distortion ratio is also 60 by 46 because you have made 46 into 60. Here 46 became 60 because of the east-west distortion, and then we made this 46 into 60 and introduced the north-south distortion. So, and the distortion ratio we maintained so that the shape is maintained. Okay, and this ratio is same secant of latitude. Okay, now how to solve this distance measurement problem? Okay, so for that we'll have to modify the latitude scale. So here 1 minute of latitude or 1 minute of distance, 1 mile of distance was 1 centimeter. Distance is measured on the latitude scale. Okay, and because the latitude scale is over here, you can see it is same. The longitudes are converging, so hence we have to measure the distances on the latitude scale. Okay, so now "60 centimeter" is representing 46 minutes. All right. Whether in departure terms or whether in DLAT terms. Okay. So, or let's write it the other way around. Okay. 46 minutes is equal to 60 centimeters. All right. So now how much will be 1 minute equal to? Or let me see. Okay, let's do this only. 60 centimeters is equal to 46 minutes. Okay, so now 1 centimeter will be equal to 46 upon 60 minutes. All right, so that will come around, yeah, okay, so 0.76 minutes. Okay, so now my scale has changed. Now 1 centimeter is equal to 0.76 minutes, or other way around also you can do it, like 46 minutes is equal to 60 centimeters. So how much is 1 minute? It will be 60 by 46, which is 1.3 centimeters. All right. So I have to redefine my latitude scale so that my distance measurements are correct at this latitude, at 40 degrees north latitude. All right. So my new latitude scale will be 1 minute is 1 minute is equal to 1.3 centimeter. So that is the reason why, as the latitude on the chart you see, the minutes, the gap between minutes keeps on increasing, because 1 minute is occupying more number of centimeters. Earlier 1 minute of latitude was only occupying 1 centimeters. Now 1 minute is occupying 1.3 centimeters. So here, if 1 minute was only 1 centimeters, here 1 minute is slightly larger. This is 1 minute of delag. Here this is 1 minute of delag. So now, because of this reduction, now 60 centimeter, when we measure by this scale, we will read it as 46. If you take this scale, 1 minute is equal to 1.3 centimeters. When you measure 60 on this scale at this latitude, you will read it as 46 miles. Okay. So from here only that formula comes, that latitude scale is equal to longitude scale into secant of latitude. So whatever was longitude scale, 1 minute is 1 centimeter. Okay, so how many minutes, how many centimeters are there in 1 minute? So 1 centimeter, and then you take secant of latitude, secant of 40 degrees, and you will get how many centimeters are there in 1 minute of latitude. All right. So now this is how we have to define our latitude scale at different latitudes. For and why we have to do is because solving our problem of distance measurement. Because of this distortion, east-west distortion and north-south distortion, our scales change. As the latitude increases, the distance latitude scale also keeps on changing to accommodate for this expansion. Yes, and by the way, this distortion, that north-south distortion, this is actually DMP, difference in meridional parts. So now we'll just go further into meridional parts. So what does meridional part represent? Meridional parts represents this north-south distortion only, that we are purposefully putting into the Mercator charts to keep the orthomorphic property. So this distortion is represented by DMP. All right. And now what are meridional parts? Now we have seen this distortion at a particular latitude. Okay, 40 degrees north latitude. We were trying to construct a chart for 46 miles of a square, and we understood how the distortion works. Now from the equator, this distortion keeps increasing. Over here also there will be certain amount of distortion in the ratio of secant of latitude. Above this also there will be certain distortion. Above this also will be there certain distortion, and this distortion is at every level, and every level it is getting stretched, and as the latitude increases, the stretching also increases, the distortion increases. So what does meridional parts give you? Meridional part of any latitude, meridional parts are tabulated in your traverse tables, and they are for all latitudes, right? So what does it indicate? It indicates the level of distortion that has happened, the amount of distortion, accumulated distortion that has happened up till that latitude. Suppose if I find out the meridional part of 40 degrees, then I'll see a value which has taken into account the distortion at each minute of latitude, because everywhere there is a distortion, and we have to, if we are making a chart from equator till here, I need to know all the distortion. So that is a sum of, it's an integration of distortion at each level from 0 till that latitude. All right, so that is where the meridional parts come into effect, that it gives you that distortion readily available in a table. So when I take the distortion at this level and the distortion at this level, and we subtract that values DMP at this latitude and meridional parts at this latitude and meridional parts at this latitude, and we subtract, we get the DMP. What is that DMP? That DMP is the remaining distortion for that much of DLAT, because you have taken the distortion from here till here, and then you have taken the distortion from here till here, and you have subtracted this distortion. So what the distortion remaining is? The distortion for this DLAT, which is relevant for you, for your chart, for which area you are constructing. Okay, so that is what meridional parts are. Okay, so I hope this gives you a glimpse into this concept of departure and meridional parts, and how we go about developing Mercator charts. So this was basically a conceptual understanding of how we need to develop Mercator charts. What are the problems that we face while transferring data from the globe to the paper chart, and how we address those problems. Okay, whether it is a problem of taking bearings, or later on the problem of measuring distances. All right. Okay. Thank you, gentlemen. I hope this gives you a good idea of the subject. Thank you.